Hey everybody. Today, what you can see at the very top there is we're going to talk about family of functions. Now, this is a particular topic, it's a classification of things, and it's really meant to be an introduction. There's a lot of new terminology on this first screen, so I want to make sure that I lay out the intent of today. We're going to talk about what a family is, and in particular, how it pertains to what we've been working on. So I don't want you to get lost in all the terminology you see here, but rather let's take it with what we've been introduced to so far this unit. So let's take a look at the first statement. Polynomial functions, those are all the functions we've been dealing with. Polynomial functions have the same x-intercepts or roots and are vertical stretches of each other. Functions that do both of those things belong to the same family. And they have equations that are or can be written in the form that you see in green. Y equals a times f of x. Now, I'm introducing some new terminology there, some new notation. Really all f of x represents is a symbol. It's a name, and it's a name for a function. I used f because it's the most common one, and that function is probably made up of x's. That's what we've been working with the whole time, so it's f of x. So let me just nail down that statement again. If you have graphs that have the same x-intercepts, or roots, whatever name you want to use for them, the same x-intercepts, and they're just stretches of each other, vertical stretches of each other, then they would be said to belong to the same family. And we could write that equation as y equals something times a base function. Okay, that's a lot of new terminology, and that's a big statement. I think if we break it down with an example, I think it'll help. You take a look, and I have given you 3 different functions. You see in that list, I've called one of them f of x. Another one, g of x, and the last one, h of x. I can't call all of them f of x because then they all have the same name. It's not as easy to talk about it. So by calling them different names, I can talk about them quick. F of x is x plus 3, g of x is 2x plus 6, and h of x is 3x plus 9. We would say that all of those functions belong to the same family because they each have the same root or x-intercept at -3. How can you tell? Well, if you took each one of those values, x plus 3, and you set it equal to 0, or you took 2x plus 6 and you set it equal to 0, or you took 3x plus 9 and you set it equal to 0, the outcome being 0, the output being 0, then you would notice each one of those would have a solution of x equals -3. Okay? Let's jump up to the purple. The purple is the key. That is, I could rewrite my red and green functions to look different. If you notice, if I common factor out a 2 in my g of x, then I get 2 times x plus 3. And you'll notice there's the same x plus 3 as what I saw in my blue function, f of x. Well, let's take a look at the green, the h of x. If I common factored out a 3, then I have the same thing again. Maybe my purple makes more sense now. I could write each one of those equations in the form y equals a times x plus 3 if I just say that that a has to be a number. You know, in the red case, in G, it's 2. In the green case, it's 3. So that's what it means to be a family. You could write them all with the same factors that lead to the same x-intercepts. You can now see why x equals -3 is a solution because they all come from a factor of x plus 3. Okay, there is our family notation. Now, I want to switch gears a little bit and see what does that look like as a graph. If you take a look, I just put on a quick sketch. You'll see a set of axes, and I have put on my blue F, my red G, my green H. You will notice that each one of those graphs are vertical stretches of the other. If F was x plus 3, then it has an x-intercept at negative 3. But my G was now 2 times x plus 3. What that means is, and we should all be good, that an a value multiplied out in front of my function, is going to provide a vertical stretch for that function. And so what you would see then is I need to double the distance from the x-axis. Now, it is a sketch, so it's not exactly great, but I think we get that idea. That means wherever my blue is, double it, that distance, to get my red. Okay, if I look to do the same thing now, but with my green function. On my green function, we know that h of x is 3 times x plus 3. So what that then means is whatever my x was, I don't know, I'll pick a value in here. Whatever that distance is, I need 3 times it to produce the green. I have a vertical stretch by a factor of 3 to get to my green function. You'll notice every single one of those functions crosses my x-axis at negative 3. If I'm just vertically stretching them, then anything on the x-axis will not move. Okay, why are we talking about this? Because I want to start to look at creating a bunch of functions that all deal with the same family, and us getting some practice about how to take a family of functions and make it a very specific one. Okay, so let's just sum up at the bottom of the page. Therefore, y equals a times x plus 3 is going to represent the equation for the family with one x-intercept. That is super, super important. One x-intercept, that being negative 3. That equation does not represent all functions with an x-intercept at negative 3. No. If it has x-intercepts at negative 3 and then a bunch of other x-intercepts, it is not a part of this family. It can only have one x-intercept. And so what we can do is we can use a very generic stretch factor of a to represent all of the functions with one x-intercept at negative 3. So that purple equation that you see up top would be the equation for the family. Okay, I think we've got some stuff summed up. I am not saying that you should be sitting there going, yes, I know exactly what I'm doing today. In fact, you should probably be a little lost. I've introduced you to some new terminology. As I mentioned earlier, what I want to do now, I want to get good at using it. Okay, take a look at the first problem. 1a asks you to create the equation for the family of functions with one root of 4. Okay, what I can do then is I can use a generic output. My generic output is going to be y. I'm talking about one equation because I'm creating the equation. And so I might just go, no thought. Outputs are y. There's my y equals. Well, if the equation tells me, or if I'm told that my equation has one root of 4, then it's important for me to know that that root of 4 must have come from a factor of x minus 4. I think we should be good on that if we go back to our review from Unit 3, when you took roots and you worked backwards to build your equation. Okay, the question said create the equation. Right now, that equation is a very specific one, y equals x minus 4. For me to make it the equation that represents the family, I just put in a generic stretch factor. Now, I'll be honest with you, we don't care whether you use A, B, K. A and K tend to be the normal ones we see. Just don't use X. You cannot use the variable of your function. It's going to have a different meaning to it. There you go. I am totally good with you giving me that equation. I am not going to demand that you then dictate that A is a constant by stating that restriction. You don't need that. If you give me y equals A times x minus 4, then we are good. So hopefully not too bad, and you're looking at that and probably going, okay, this isn't too bad. This isn't too bad. I think I got an idea. Okay, let's take a look at problem B. When you address problem B is now going to ask you to create the equation for the function with a root of 4, which we just did. But now I'm asking you to make sure that it passes through that point. Okay, I'm going to go back and I'm going to build this like it was from the beginning. I'm going to create an equation. It has a root of 4, so it must come from a factor of x minus 4. And I need to have a generic stretch factor to represent all of those functions within the family. Okay, if I put on a quick set of axes off on the side, and I now just did the purple, you should be good to see that we would have a y-intercept at -4, and this would be a line. It would be a line with a slope of 1. We should all be pretty comfortable to produce that graph. I'll put arrows on the end. I am good. That is a very specific graph, my purple. And what that purple would actually represent is as if the A value was 1. Right? If my A value equaled 1, then 1 times the purple is still the purple. There we go. I think by seeing the graph, that's going to be helpful to us. Because what part B now asks me to do is not build the purple. Clearly, that purple does not pass through the point -1, 5. Look, it's all the way up there. So what I need to do is build the equation that's going to go through that point. Now, a couple quick things. You may, in your quick thought, go, hey, well, why don't I just shift that graph and shift it up so that it goes through that point? And I want you to notice that as soon as you start to shift up that graph, you're going to lose the most important feature of that graph up until this point. It has to have an x-intercept at 4. Notice, as soon as I shift that purple line up, I'm going to lose that key point. It's gone. So, let me put that quick set of axes down again. Let me very quickly and crudely extend that graph back. This value of 4 must be maintained. Okay, so how can we now get rid of that purple graph? The purple one is clearly not correct. And maybe rather than say get rid of it, how can I change that purple graph to now still go through that blue x-intercept of 4, but also pass through my green point? If I were to draw my graph, I think we should be comfortable to be able to draw it. That would satisfy the problem. An x-intercept at 4 passing through that point. So the question then becomes, how do we get it to do that? Well, take a look back at my equation And take a look at that red value that we stuck out in front. That red value represents something that would vertically stretch our function. So what I need to do is change the shape of my graph. I'm not talking about changing it from being a line. No, remember, shape means slope. Shape can mean direction. So what I'm going to do is I'm going to actually solve for my A value. I can use my A value to force my graph to become the green one. Okay, how can I do that? Well, take a look at your purple. Right now, my purple represents my generic equation. It's for my family. Now, if I wish that it was going to go through that green point, then I'm not going to wish. I'm going to make it go through that green point. What I'm going to do is I'm going to sub in the point that I wish my graph passed through. I'm going to force that point to be on my graph. Remember, all a point is the relationship between an x value and a y value. That's all it is. So let's sub that relationship in and make it happen. So if I was to sub my y value of 5, then I have to make sure that my x value is -1. You'll notice I replaced my x with -1, replaced my y with 5. What that just gave me was an equation. And if I were to follow BEDMAS, I get an equation with one variable in it. Look, it's just a. I could divide out my -5, and I just solved for the specific a value I would need to make that shape go through that point. So all I have to do then is sub it back in. Okay, therefore, the specific equation has to have an a value of -1 and the factor x minus 4 to still maintain the same x-intercept. There you go. Now, that process that I just went through is one that we are going to do 1,000,000 times. The idea of, if we need to, let's make our function pass through a point. Okay. I'm hoping that that was a pretty good walkthrough, and I'm hoping that you got a little bit better sense of where we're going to go. Now what I want to do is I want to start to jump into some more complex problems. Okay, let's take a look at problem 2, and I want you to look at problem 2 holistically. That is both part A and part B. Let's read problem 2A. I want you to create the equation for the family of functions that have -2 and 3/5 as the only roots. Then in question 2B, I want you to create the equation for the function that has -2 and 3/5 as the only roots and now passes through a particular point. I want you to be able to see both problems so you can see the difference. In problem A, I am asking you to come up with the equation for the family. That means generic. In problem B, I'm asking you to come up with an equation that passes through a particular point. That is very specific. So I'm hoping we can see the difference between the two. Okay. I want to walk through question 2A because I don't think we're there yet on our own. I think we're getting there. Let's take a look at 2A. I'm going to create an equation. I'm going to use my generic output. There's my y equals. Now, it's told me that I have particular roots. Well, let's zero in on the first one. If I have a root of -2, then it must have come from a factor of x plus 2. Nice. Well, I'm also told that I have another root at 3/5. I could, if I wanted to, write down that, and that is 100% correct. I just wouldn't if I were you. I'm introducing fractions. It's going to make my life uglier later on. And in some areas, it would be considered bad form. So rather than writing down the green, I'm going to simplify and write everything with integral coefficients. What that just means is I'm not going to write in fractions. I'm just going to use integers. So rather than have x minus 3/5, I'm going to have 5x minus 3. Now, if you're looking at that and you're going, I don't see how we get that same thing, let's take it 2 steps. If I get a little confirmation, 5x minus 3, if I'm looking for an x-intercept, that means the output was 0. So I could solve that, and notice we match up with the green. The other thing I could have done was take the green and work backwards. If x equals 3/5 is one of my roots, then I could multiply out the 5 and now set it equal to 0 because it was an x-intercept. Either way is going to get me to the best factor, 5x minus 3. Okay, that is a very specific equation. It does not represent the family. Now that those 2 roots are represented, all I need to do is put in a generic stretch factor and I am good. There you go, 2A completed. Okay, I think you're at a point where you could maybe come up with a solution to B. So I want to give you that opportunity. Now that we've built the equation for the family in A, now I want you to come up with a specific one in B. So here's a chance to pause the video and give it a shot on your own. Okay? Pause it now. Okay, we're back. So I am hoping that we know we can make it a very specific equation by just forcing the curve to pass through the point, which means I'm going to sub in that relationship. So my y value is 4 when my x is -3. It just so happens I have 2 spots where I could sub in an x value of -3. And there we go. You'll notice I replaced both of my x's with -3. In the second factor, I wanted to multiply it out to pick up the pace a little bit. Now, I created an equation with just one variable. I'm going to go through and try to simplify that as fast as I can. I can collect on the right side. -1 times -18 is 18. That's all times A. I'm running out of space. I can now divide out my 18, which leads me to a reduced value of 2/9. So the only thing left for me to do then is to actually write the equation of the function. So that specific stretch of 2/9 with those factors gives me the equation of my function with those 2 roots and now passes through that particular point. How well did we do? I'm hoping we were good on being able to sub in the point and solve. Okay, we got one more problem to go through, and this one's going to be a bit of a doozy. Okay, I want to just leave this one with you. It provides an opportunity for you to get some practice at dealing with a little bit of problem solving. I would like you to create the equation for the family of functions that have -1, 3/2, and -1/7 as the only roots. And then, once you've dealt the family, now make it very specific and make it pass through that point. We'll see if we get down to the same thing at the very end. We'll see if we match up. Okay, I want you to pause the video now. Okay, we're back. So the first thing I need to do is make sure that I satisfy all my roots. If I have a x-intercept at -1, then it must have come from a factor of x plus 1. If I have an x-intercept of 3/2, that must have come from a factor of 2x minus 3. And if I have a root of -1/7, then that must have come from a factor of 7x plus 1. Those factors represent all three roots. Now I just need to stretch it. There is my family. That satisfies the red. But I now need the specific blue case. So I could sub in my point and force that graph through. If I make the substitution of 1 and I simplify as I go, so I'm not just generically writing down a 1 in place of all your x's, I hope we would be comfortable to come in on that blue line. Okay, let's simplify everything we have. On the right side, I should have a -16a. Now for me to divide out, I need to divide out a -16. Well, a negative divided by a negative is positive, and 8 divided by 16 is 1/2. I'm hoping we matched up, and therefore the only thing left to do is write in my stretch factor with those factors, and there is the equation that now passes through 1, -8. Okay, I'm hoping that that one was pretty straightforward with you, and I'm hoping that you got some experience working with a family. Really, all we did today was introduce the terminology of a family of functions, and we were able to relate it all back to stretching a function, a vertical stretch. You learned today, or I shouldn't say learned, we extended this from what we had previously covered to now being able to force graphs through points. We can now get to the point where we can build functions very specifically. Okay, your job, jump in and get some practice with family of functions today. Best of luck.